So my name is Jonas Ohland, and I've been working in the field of adaptive optics for high power laser systems for a while now. That's actually also the field where I did my PhD. But over the last couple of years, we did something new in the frame of the ARTAO project. So ARTAO stands for the Apollon Real-Time Adaptive Optics system. And to my knowledge, that is one of the first attempts, if not the first attempt, to actually employ real-time capable adaptive optics system in the frame of these very high power laser systems. So here in the title, I quite boldly state from telescopes to fusion power plants, where the fusion power plants are obviously some future prospect where this technology may lead us. I will comment on this during the end of the talk, but the first part here from telescopes, that is actually encapsulating the fact that this ARTAO project was kind of a technology transfer project from the field of astronomical instrumentation. And for that, we partnered up with the CACAO team. So CACAO, that stands for Subaru Coronagraphic Extreme Adaptive Optics. And this team, as the title says, is responsible for the adaptive optics system at the Subaru telescope. So this is a photograph of the dome interior of that telescope. It's located on Mauna Kea on Hawaii, and it has a primary mirror of a diameter of 8.2 meters and the height of that blue structure here, so the telescope itself is 22 meters, and just for comparison, that's that little figure there, that's me when I visited this facility to learn about the adaptive optics system. Um, and these people, they're really masters of their craft. So they are developing adaptive optics for the purpose of exoplanet imaging. So where they basically block out the light of the central star and try to get direct imaging of the planets that orbit other stars. So it's not getting much more professional than that, and we hoped to get some insights on how they do that and apply that in our field. So in this talk, I will start with a little motivation and will also introduce the Thrill project, which is kind of the umbrella project which funded this whole research here. I will then get to the Apollon laser system and discuss the beam stability issues that we had there, which kind of sparked this whole project here. And then we will get to the nitty-gritty details of the adaptive optics system itself. So I will tell you how we designed this thing, how it looks, and how it performs in the end. And we'll then close with some future prospects for this technology. So I brought you here the IQWIL world map on ultra-intense lasers. So I'm sure a lot of you already saw that in the past. This is the 2009 version of high-power lasers worldwide. And if we take a look here to the map around Europe, we see that there are some high energy laser systems around there already. So for example, we've got the Vulcan laser at RAL, Orion at AWE, Lully, of course, and some more. And if we skip forward a decade, we see that there's a whole lot more activity here. And if we browse through all these names, we see that there is like an emphasis on shorter pulse lasers, so these ultra-intense laser systems. Nonetheless, we recognize that there is a growing demand for higher pulse energies. For example, if we look at the Aton laser system, the L4 beamline at Eli beamlines, we see that despite having short pulses, we still want higher pulse energies, and we want them at higher repetition rates. So as a person who worked with neodymium glass-based systems for a while now and faced limitations of one shot only every 90 minutes. I know what I'm talking about. So having more shots per unit time is definitely something that we want in order to gain more statistics in the research that we're doing. So there is obviously a growing interest, and that is expressed, for example, in the Thrill program. So Thrill stands for Technology for High Repetition Rate Intense Laser Laboratories, and that is an EU-funded research program that solely focuses on technology for this new generation of laser systems where we want to have high pulse energies at high repetition rates. So that is running for 2 years already. There's 2 more years to come. We've got a budget of about 10 million euro. There are 9 partners in total. And there are different topics that are investigated within Thrill. For example, we've got amplifier design, coherent combination, coating of large optics, and of course also beam quality and beam transport, which is the work package that ultimately funded the work that I'm talking about today. Let's get to the project finally. It makes sense to start with introducing the Apollon laser facility. So Apollon is a titanium sapphire laser located in France with the goal of delivering 10 petawatts by having pulse energies of 150 joules per 15 femtoseconds at one shot per minute. This is really one of the few laser systems that want to join this rank of the 10 petawatt class. Um, and the way that Apollon does that is basically just having a bunch of titanium sapphire multipass amplifiers. So what I brought you here is a rendering of the amplification area of Apollon. So that's one of the laboratory rooms in the facility. The front end pulse enters the room over here. Then we have this large amplifier table here where we've got a couple of these multipass amplifiers. You recognize them by this bow tie structure here. We've got three different sizes on the table that bring up the pulse energy to 30 joules in total. And after that, we get to the last and largest amplifier, which is called Amp 300, or the 300 joule amplifier, which sends the beam 4 times through this very large titanium sapphire crystals. So the crystal has a diameter of almost 20 centimeters. The beam itself only 14 centimeters, but if we look at the size of the structure, we realize that this is with 12 meters in length, that this features 50 meters of propagation through laboratory air. And combined with the fact that we've got 14 centimeters of beam diameter, that means that we are very vulnerable to density fluctuations in the laboratory air. So, for example, heat exhaust from power supplies and so on. All these things will have a dramatic impact on the beam quality. And I mean, we knew for a long time that beam stability is an issue at Apollon while we were in this ramping up phase. But before we started this project, we actually characterized what happens here. And so what you can see here is a real-time playback of the wavefront, how it looked before we did any countermeasures. And as you can see, the focal spot that we get from a Fourier transform of the wavefront here performs some wild dance here. So we get Strehl ratios from a close to perfect beam down to only 0.2 within a matter of seconds. So needless to say, even if you shoot once per minute and not only once every 90 minutes, that is not ideal for research applications or even inertial confinement fusion research or something. You just need a more stable beam than that. Um, we also characterize the mean speed of the fluctuations of this wavefront to get an idea on how fast this evolution actually carries out. And if we look at like individual pixels in the wavefront map here, we realize that the jitter that we get here has a saturation frequency or a cutoff frequency of about 70 hertz, which is very fast considering that we are located inside a laboratory and not in plain air outside or something. So yeah, we needed to do something about this. The very first thing that was done is that we constructed a proper beam housing here. So that was actually a challenge because we not only have 4 main laser beams entering the crystal, but also 7 pump laser beams that enter this crystal from above. So they are not shown in this drawing here. But that basically meant we needed to settle to some sort of like a double cone structure that tries to keep out the air turbulence, which certainly helped a lot, but still we failed to get to the specifications that Apollon was meant to deliver. So we ended up with a situation where we actually needed to employ some sort of active stabilization method in order to keep the beam as stable as it should be. So now we have an issue here because in our community, nobody really has a lot of experience with working with complex real-time capable systems like that. So there were not a lot of people who I could ask how to do that. So the natural consequence was to turn to the experts and ask how they are actually doing it. So here again, we've got a photograph of the Subaru telescope, this time from the outside, and they're using their nice artificial laser guide star laser here, which excites sodium ions in the upper atmosphere to get some control signal for the wavefront sensor. And we know that astronomy has several decades of experience with real-time capable adaptive optics. So actually, we could omit this real-time statement here because in like every other field except of ours, adaptive optics includes real-time capability. It's just that if laser people talk about adaptive optics, they are usually happy with mirrors that are semi-static and are just for optimization of the beam. That's why I always explicitly state real-time adaptive optics here. So we decided to draw some inspiration and technology from them, and the people at the Subaru Observatory, so the CACAO team, were so kind to help us here, and so bigger shout out to them. Without them, this project would not have been possible. And now I want to take you through the entire system and tell you how we actually did that. So on this slide, I brought you a little cartoon, a very simplified cartoon of the Apollon laser beam line. So we've got our main laser source here. We send that onto our deformable mirror. So this one is a relatively small deformable mirror earlier in the chain because smaller mirrors can run faster because all the resonance frequencies of the glass membrane are just higher. So it's less likely that we actually excite the deformable mirror, which should correct instead of make things worse. Then the beam passes through the last two amplifiers of Apollon, so the 30 joule and the 300 joule amplifiers, and also picks up on all the air turbulence that is in between. And right before the beam then enters the vacuum of the compressor, we take a leaky mirror and we put some of the energy onto the wavefront sensor to close our loop. Now, obviously, at this point, we understood that this will not work because our main laser source here is pulsed. So if Apollon operates regularly, we get 1 shot per minute, which is hardly enough to do real-time beam control. So the first thing that we did is to draw some inspiration from astronomy and implement our own little laser guide star. So of course, we did not use a sodium laser for that, but we have a continuous wave pilot beam that is detuned from the central wavelength of the Apollon laser itself. So that is a 905 nanometer fiber coupled diode laser here. Um, and by doing that, we can just use a dichroic mirror to inject it into the laser beam line and make it co-propagate with the main beam. Then we have some beam transport, which transports most of the power of the witness beam here. So the entire transmission of the pilot beam is about 10%, which is not perfect, but it's definitely enough to get the rest of the energy into the wavefront sensor here and close the loop on that. And now we are really in a good position because we can have we can acquire frames as fast as we like because we have continuous light available here. And by using sufficient spectral filtering here, we could even shoot the main laser beam without risking to burn the wavefront sensor. So we're kind of independent from the operational state of the entire laser system itself. So concerning the adaptive optics system itself, what we did for the wavefront sensor is to use a fast PCIe camera from Ximea. So that is basically a camera that does not need a frame grabber. It directly plugs into the computer and streams the pixel data onto the working memory of the computer. And if we consider only the region of interest of about 5 by 5 millimeters, which is the size of the beam at the sensor, then we could get up to 7 kilohertz of frame acquisition. Then we equipped this camera with a microlens array to turn it into a Scheck-Hartmann sensor and did all the evaluation then on the graphics card of our real-time computer. The real-time computer itself could be described as a really nice gaming computer in some sense. So we've got a 16-core AMD processor and an NVIDIA RTX 3080 graphics card, which does the main number crunching, so evaluating the wavefront sensor, matrix multiplications, and so on. But the most important part about this real-time computer is that it runs on CACAO. So CACAO is compute and control for adaptive optics, and that is an open source adaptive optics software which was developed by the CACAO team on Hawaii. Again, I can't thank these people enough that they trained us on how to install the software, how to operate it, and also how to manipulate it and modify it in order to fit to our requirements here. So after we ran all the data through CACAO and we get the control values for the deformable mirror, we have to send them to the mirror, of course. And that is a plain bimorph deformable mirror by dynamic optics. It has an aperture of 60 millimeters, the 96 actuators, and we update the shape of that mirror at 1.3 kilohertz, which is definitely enough to reject the aberrations that we want to control here. So this is the plain setup here, but there are some things that we should consider before we just plug it into the system and switch everything on. And the things that we want to do here is first we need to characterize the loop characteristics, of course. So just put it onto a test bench, see how the whole system behaves, what it can do, what it can't do. then we need to make sure that there is sufficient correlation between the main and the pilot beam. I mean, in the end, these are two different laser beams. If you want to stabilize the main beam, we should definitely make sure that the pilot beam is picking up the same aberrations as the main beam. So this is at this point only an assumption, so we should measure that. Um, One more thing that is really important is to see what happens when we actually pump these amplifiers here. So if we do that, we still get some residual gain on the pilot beam, even though if it's a little bit off spectrum here. Um, we should make sure to still keep control over the beam and not burn anything by doing that. And the very last thing is, of course, to characterize the performance that we get when we plug the system into the laser chain. So on the next slides, let's just go through these 4 points here, and let's start with the loop characteristics. So we set up a test bench and wanted to investigate the spectral gain of the system. So basically a measure on how well the adaptive optics system can cope with different speeds of aberrations that we have there. And what we basically did is that we artificially injected some turbulence into the system by just offsetting the deformable mirror channel values and then still closing the loop and seeing how well the system can cope with that. And by that, we got this nice graph here where we've got the frequency on the x-axis. That is the frequency of the aberration evolution. And on the y-axis, we've got a gain factor for all the frequencies. So that basically means that we have a high rejection or high damping of all slow varying aberrations here. So if we have something like a beam drift or something, that is, of course, very easy to compensate for. So the adaptive optics system just can follow that, and we have a very high rejection. If we increase the frequency and then we look at 10 hertz oscillations, for example, we see that we still have some rejection happening, but it's definitely not as good as the one for the slower ones. That's just natural because our system has a limited speed. And then at some point, there is this crossover frequency beyond which we actually get a positive gain, which means that we amplify aberrations instead of rejecting them. And that is obviously something that we need to avoid. Therefore, when designing such a system, you need to make sure that this crossover frequency is well above the maximum frequency that we actually have in your system. And we saw on our test bench that this is the case. So even when we had no beam cover whatsoever in place, the maximum frequency that we got was about 70 hertz. Now we've got a nice beam covering, which means that things are evolving slower. So this system is definitely fit for beam stabilization as it is. Just one side note here, the dashed lines, these are actually simulations. So we set up a little model of our adaptive optics loop in Laplace space just to check if we understand what's going on and if the loop performs as it should. And as you see, the match is quite nice here. So that's definitely good news, and we can trust that our system will at least not break anything. So the next test that we needed to do is to verify that our main beam correlates well with the pilot beam here. So we've got two beams propagating simultaneously through the Apollon laser system, and we can place a wavefront sensor in both of them. So what we see here on the upper side is the wavefront recording of the main Apollon laser beam recorded at 5 hertz. So that is obviously only the front end, not amplified pulses or anything. And simultaneously, we placed our fast wavefront sensor in the pilot beam here. And we basically just picked the frames of the high-speed wavefront sensor that matched the Apollon laser beam timestamps the best. And as we can see, by sheer eye, there is some nice correlation between them. So they basically look like it's a vertically mirrored image of each other. But we can do that a little bit more quantitatively by just looking on how one pixel in one wavefront sensor space correlates with all the other pixels in the other wavefront sensor space. And from this correlation map, we can then basically infer a linear transformation between these two spaces and could interpolate, for example, the pilot beam to match the orientation of the Apollon wavefront sensor here. And if we subtract the two, then we get the difference between them that is basically the error that we're doing in this whole process here. So we see with the naked eye that the difference map here features a much lower amplitude than what we get in the actual wavefronts here. That is a good sign. And if we look at the RMS over time, so on the x-axis we've got the time, on the y-axis the RMS of the wavefronts, then we can see that the pilot beam and the Apollon beam, they look very similar. So this is the green and the blue curves respectively. And if you look at the RMS of the difference, which is the red line here, we see that this is consistently below the other two curves, um, which means that it largely fits. There are some errors still, so this is not zero here. But if we look at the differences in the difference map here, then we see that these errors are primarily in high spatial frequencies, which has some implications. So, for example, we know that we have different spatial samplings between the two wavefront sensors here. We may have a slight temporal mismatch because really the pilot beam wavefront sensor was not triggered. We were just selecting whichever frame was closest to the timestamp of the Apollon wavefront sensor. We do have some signal to noise ratio issues, and of course we did an interpolation here. So all these things just add up and say, okay, it seems to be plausible to just correct the pilot beam. If we do that, we expect to have a much, much more stable wavefront in the main beam as well. So it will at least remove all these high amplitude, low order aberrations from the beam. So the next thing that is very important, and this is the last point that we needed to investigate before actually setting the whole thing into the system and see how well we can stabilize the beam, is what happens when we pump the amplifiers. So what we basically did is to switch on the adaptive optics loop and see what happens when we flash the amplifiers here. And on the x-axis, you've got the time scale. It's all zoomed in. So from it's about 25 milliseconds window here. On the y-axis, we've got the RMS again. And what we can see is that for all the negative times, we've got a nice and stable and flat wavefront. And at t equals 0, we then flash the amplifiers. We bring energy into the crystals, and that leads to an amplification of our pilot beam here. And this amplification is not necessarily dangerous for the wavefront sensor. So it's a continuous wave beam, so there's not a lot of energy in it. Still, we get some oversaturation of the spots on the Shack-Hartmann sensor camera. And of course, the evaluation algorithm kind of misinterprets that. I mean, what other chance does it have? So we get something that roughly looks like tilt here, which is certainly not real because we see that the wavefront is nice and flat immediately afterwards again. But what is very interesting to me is that if we wait some more milliseconds here, then at some point we see the attack of the adaptive optics loop, which tries to compensate this tilt that was measured before, even though it was not real. So we get the spike here, and the ratio between these two spikes is actually like the feedback gain of the adaptive optics loop. So that was very interesting for me to see. It's nothing to worry about though, because we can see that the loop rings back to baseline very fast, and this impact of the mirror trying to compensate something which is not there happens way after the shot has been delivered, or the hypothetical shot has been delivered. So this is really not a game breaker. It's for us, it's just good news. We can just keep the loop running, and we do not need to worry what happens on the shot then. So now that we have all the characterization done, let's see what the system actually does for the stability of Apollon. So here on the left side, we've got a time series plot again, this time over the course of 2 minutes, where we switch on the adaptive optics loop at t equals 0. And we can clearly see that while we have some wild Strehl ratio fluctuations on the x-axis, we kind of snap to almost perfect beam right after the adaptive optics loop has been switched on. One disclaimer that I need to make here, that this is not the actual Strehl ratio that we're getting in the target chamber. This is just relative to the beam reference that we use for the adaptive optics loop. So if you want to think about it like that, if you remove all the static aberrations perfectly from your beam, then you will get this Strehl ratio in the target chamber. If not, then we still have a perfectly stable beam, just a little bit offset maybe into one or the other direction. On the right plot here, I think this becomes even more evident. This is actually the same data as on the left plot, just in histogram view this time. So we've got the Strehl ratio on the x-axis this time, on the counts on the y-axis. And we can see that the red curve here, which kind of resembles the data without the adaptive optics loop, features all these different Strehl ratios in different amounts here and goes down to 0.65. But with adaptive optics loop, we are basically having not a single wavefront, which is worse than a Strehl of 0.96. So that is very good news. That made us very happy to see, which means that this work has probably not been in vain. However, we also need to be cautious about that because this is only the short-term performance, as I wrote here in the title. So that works if we have only a short time window to look at it, but things get a little bit more ugly if we try to zoom out and see what happens if we actually run the system over the entire shot day. Um, so here I've got another time series plot, this time over the course of almost 2 hours. And on the y-axis, we've got the wavefront RMS again. And some things that we see here is that in the beginning of the operation, like for the first 30 minutes, we've got a nice and stable operation. So just like the one that we saw on the last slide. For the next half an hour, though, we see that there are these single points here where the wavefront suddenly looks much, much worse, which is certainly not ideal. And after the 1 hour mark, things get completely crazy, and we have these extended and very, very mad series of instabilities here. So these streaks of instability, which basically make the beam completely unusable for this time here. So that is very worrying. However, we know where it comes from. This is due to something that we call misregistration. So misregistration is basically a word that describes the effect that happens when the image of the deformable mirror on the wavefront sensor image. So this is an image of the wavefront sensor, and I try to indicate the aperture with this green circle here. So if the image of the deformable mirror shifts laterally on the wavefront sensor here, and what that does is basically that the image position of the deformable mirror actuators does not match the position of the actuators when we took the mirror response. So that just means that we are controlling the mirror with the wrong input, and that, of course, leads to instability, um, which is something that we definitely do not want in our system. So this is not good in two ways. First, of course, we've got a bad beam, but the second thing is actually much worse, and that is that in this unstable state, the deformable mirror creates so large strokes that we get these hotspots in our near field here. So these are three example near fields of the Apollon laser when the mirror is unstable. Um, and you can see that we've got these swimming pool-like patterns here. And if you deliver a shot when your loop became unstable, then this is basically a death sentence for the compressor grating. So you really, really, really want to make sure never to deliver a shot when the loop is unstable. Luckily enough, if you know the cause here, so the misregistration, the quote unquote only thing you need to do is to find a smart way to do beam tracking. So to make sure that the image of the deformable mirror is always staying at the same location on the wavefront sensor, and this does not happen. So we verified that, sadly not in the plot here, but by tweaking one of the mirrors, which is not in the conjugate plane of the deformable mirror, basically to move the picture back where it was, so the image back where it was, and the loop was immediately stable again. So that would be the way that you need to go in order to make it permanently stable. So now let's get to the outlook of that. So once we solved all these issues, what could we do with that? And one thing that was like a very popular topic in the recent year is inertial confinement fusion. So we all know the National Ignition Facility with its 192 high energy laser beam lines, which can fire simultaneously to deliver pulse energies in the range of megajoules to compress a ICF fuel pellet. So this is now very simplified. Of course, the NIF does use indirect drive and so on, but you get the concept. And this is something that is being investigated by a lot of labs right now because the National Ignition Facility had this breakthrough in 2021 where they first had demonstrated ignition of their target, and suddenly there's a lot of interest from all over the world to join the game and try to make ICF work. So if we look at the specifications of NIF and what they achieved, we see that they did quite some tweaking, and they increased the gain of their implosions. So I think in the beginning of this year, they reached a gain of 2.4, which is very impressive. So that's a huge progress. If you want to use that in a commercial power plant, we need to get a lot further, though. So I heard numbers of needing a gain of about 100 to actually make this work. So this is obviously a long way to go. And the other thing, so there are a lot of things that are still problems that are not solved, but concerning the laser side of things, is that the shot rate is far too low currently. So NIF uses these neodymium glass slab-based amplifiers, And in order to make this implosion repeatable, they really need to wait until all the heat left the amplifiers to have a repeatable and reproducible shot delivery. That means they can only shoot 3 times per day, roughly. However, if we want to do that commercially at some point, we need to be much, much faster. That is about 10 times per second. So no one really knows how lasers that can do that will look like. But of course, adaptive optics would be a thing that can help with this. And I will talk about that in the next slide. Um, However, all these things can be addressed in research programs that pop up all around the globe. One of them is from the German Federal Ministry of Education and Research, because some while ago they published this position paper where they said, okay, we clearly want to join forces here for fusion research, and one of the approaches that we want to investigate is inertial confinement fusion. So let's pick up the loose ends here. So as I said, we need a larger gain. So what would be a way to reach larger gains? Well, there are plenty of ways, but one of them is to use a different driving scheme. So for example, if we stick with a capsule collapse, that would be a direct drive scheme where we do not convert the lasers to X-ray first, but directly shoot onto the capsule. That would be way more efficient, but it's also way more delicate. So the main reason why NIF does this indirect drive is that the X-ray field that they get in this tiny oven capsule is much more homogeneous than what you usually can achieve with lasers. So if you want to shoot with the lasers directly, then you need to have a very precise control of what these lasers are doing. That is beautifully demonstrated by these simulations that have been published by Critcher et al. In 2022. So these are basically simulations of 4 different implosions that they did at the NIF facility, where they incorporated all the imperfections that were known into the simulation and tried to see what happens. So these plots here that are actually taken from the simulations at the time of maximum neutron yield. And you can see that we have all these curled up interior walls of the outer shell that is being driven out by the fusion reaction. So needless to say, if you want to do that homogeneously, then you need very precise control of your lasers. One thing that counteracts that is that we also need faster lasers, how I said before. Faster lasers mean more heat. More heat means larger fluctuations in your laser system. So this is kind of doing the opposite of what we want with the more precise control. So you see that this is growing up to a real challenge here. And this is something that we need to investigate, and real-time adaptive optics is one central part of that. So actually, there is a program probably coming up next week that next year that depends a little bit on how the German government evolves over that time. But if this gets accepted, we will have the funds for 5 years for several researchers to research what we call adaptive laser architecture. So this is basically a new approach to rethink beam control in high power laser facilities, using a real-time adaptive optics, but also kind of integrating all different means on how to control laser quality into one unified global control framework. So I think that's it for now. Thank you very much for your attention, and let me just wrap up really quickly. So the Apollon Real-Time Adaptive Optics project is inspired by astronomy. It solves this single shot issue by using a pilot beam approach. So we use this off-spectral beam like a laser guide star in order to have a continuous feedback for our laser beam control. And with our 1.3 kilohertz control weight, we gained excellent beam stability with a Strehl ratio of variations of less than 5% in total. There are still some hurdles to take. One of them is this beam drift that we counted before, so this misregistration, where we need to find some smart way to compensate for that to keep the image of the deformable beam mirror stable, and also have some additional fallbacks, so bake in machine safety requirements into the loop, so just prevent the mirror from going crazy without anybody noticing, which happens really fast if you're talking about the kilohertz repetition rate here. And of course, this whole thing needs to be integrated into the control system of Apollon because I mean, this CACAO software has been designed by people who work every day, all the time with this adaptive optics system, and only with that. This is something that you cannot really expect from the average laser operator. So we kind of need to simplify things, break them a little bit more down, and have it integrated into the laser control system. So concerning the impact of that, we know that real-time adaptive optics is something that can greatly increase the repeatability of shots that can be delivered in these facilities. So this could greatly increase the value of data that are taken in experiments in general. So we all have this seemingly sad joke in mind that if data in plasma physics is within one order of magnitude from the model, that is considered to be precise. And I think laser stability has to do something with that. Um, but also we could enable having faster repetition rates in existing laser facilities, which would of course also benefit the output of the outcome of these experiments here. And one thing that I just said on the last slide, of course, if we want to have inertial confinement fusion running at some point with increased repetition rates, this is probably a technology that we need to develop further in order to really unlock this. So with that, that's really it now. Thank you very much, and I really look forward to your questions.